This presentation is about power analysis, which is a crucial step in any social science study. I'll be talking about a number of different elements that actually constitute power analysis. Essentially, there are 4 elements, and these are basically dealing with statistical quantities that if you know 3 of them, you can get the 4th one. Essentially, we're looking at alpha, which is the p-value, which hopefully some of you have heard about. The other piece of the puzzle is power, which is a beta value, which is actually what we're going to be focused on, is an analysis of how powerful your results are in terms of detecting effects. The third element is the effect size that you obtained, meaning how big of a difference is there between groups? Not just is there a significant difference, which is what the p-value tells you, but the magnitude of the difference between groups. And then finally, sample size is the 4th element. So we'll look at each of those as we go through the presentation, but just so you know, that's what's sort of on deck here. And again, like I mentioned, if you know 3 of them, so if you know the alpha value, the p-value that you got in your results, if you know the effect size in your results, and you know the sample size that you had in your data, then you know how powerful your study was. So to sort of put everything in perspective, what you want is to have adequate power to detect an effect. The problem is, what happens if you get a non-significant p-value? Do you throw your hands up and say, oh, well, I guess that that there is no effect that I was actually hypothesizing there would be? That may be the case, but it could also be the case that you conducted what's called an underpowered study, meaning that you didn't have enough data to actually detect a significant effect, despite it actually being a significant effect out in the real world. So what you want to make sure that you have is adequate power to detect an effect, and then if it's not statistically significant, you can say, okay, well, I know that it's not statistically significant, instead of just not knowing whether it's not significant or whether it's just an underpowered study. So we're going to be figuring out ways in this presentation to test the power of your analysis. And that in turn dictates that we have to have an adequate sample size, right? Like I mentioned, if you don't have enough data, it might be underpowered. So how do we know we have enough power? How do we know that we have an adequate sample size? And then, of course, that has implications for your design, which I'll talk about, because depending on how big how many people you have access to as participants, that will dictate, in a real-world sense, how to design your study. So we'll look at some examples of that. Now, before we actually get into the nitty-gritty of that, I want to just make one point of clarification about qualitative studies. So in qualitative studies, what you're looking for in terms of power is this concept of saturation. And saturation basically means collect data until you start to see consistent or repetitive themes emerging from your data. And this is an analog of power in quantitative studies. Power analysis is typically limited to quantitative studies, or if you're running a mixed method study, then you would have a power analysis for your quantitative portion, and then you would be looking for saturation in your qualitative portion. So typically, 12 participants in a qualitative study is an upper limit, where you hope that by interviewing 12 participants, you would get consistent themes emerging out of your interviews, out of your perhaps doing focus groups, whatever the case may be. You would hope that by the time you hit 12 participants, you're starting to see a trend. And at that point, you can stop collecting data. That's how you know that you've gotten to saturation. And so it's kind of like an iterative process, right, where you get into analyzing data from one person, you see what they said, second person maybe is consistent, third person maybe is inconsistent, and then by the time you get to 12, you should be seeing the bigger picture sort of emerge out of that. And at that point, you can stop collecting data. Sometimes it happens before you hit 12, and ideally, you would get to saturation before you hit 12 participants total. In any case, just wanted to make this clear that in terms of a qualitative study, you would never really be doing a power analysis per se. You would be looking for saturation. Okay, now with that out of the way, let's look at those 4 pieces of the puzzle, right? So first off, let's look at alpha. This is that p-value that everybody wants to sort of get from their data analysis and say, oh yes, I found that significant effect, right? That's sort of something that we all focus on, and it's a very important part of the process of analyzing your data. It's certainly not the only piece of the puzzle, though. So what is the p-value? Well, it is the probability of a type 1 error. And a type 1 error is where you incorrectly reject a null hypothesis. A simpler way to look at this is to call it a false alarm. What is your false alarm rate? Meaning, if you obtain a p-value of less than 0.05, you want to be, what you're saying is that the probability of it being a false alarm is less than 5%. So that's kind of what you want to be the case. Essentially, you want to observe an effect that is real. So what you want to avoid is this last piece here. You want to avoid observing, I put in quotation marks because you observe it based on your data, right? So you observe an effect that isn't really there. You might have this happen, but you're protected from this by this p-value of less than 0.05 being the gold standard, right? You under a p-value being less than 0.05, if you observe an effect, then the p-value less than 0.05 tells you, okay, look, if this isn't a real effect, if you're committing a false alarm, if you're obtaining a false alarm, you have a 5% or less chance that it's a false alarm. So we all agree that it's a real effect. So as long as your p-value is less than 0.05, great, you're in the ballpark and you can be sure that you're not committing a type 1 error. However, there's another side to this story, which is type 2 error. And under type 2 errors, this is where you have a value called beta, and this is what power analysis really sort of tells you is your probability of committing a type 2 error, which is missing an effect that actually is there in real life. So, and again, just like you're looking at false alarms, the flip side of it is missing an effect, right? So you have a false alarm where you observe an effect that isn't actually real. You could also miss an effect and not observe an effect that actually is there. So, for example, if you have a p-value greater than 0.05, well, again, like I said at the beginning, that might not be, it might not be the case that there is no effect. It's just that you missed it because you didn't have sufficient power, right? So that's what typically leads to misses. It's not necessarily not a real effect, but just a lack of power to detect the effect. And the bottom line is that the less data you collected, the less precise the estimate of your statistical analysis, which then means that you might actually get p-values greater than 0.05, when in reality that effect could be real, and if you had just collected more data, that estimate of the effect would be more precise, and you would actually reach significance and have that coveted p-value. It's often neglected in the literature. People always focus on the p-value, and if they get a p-value of 0.06, 0.07, they're like, oh gosh, it's non-significant, and start making conclusions about the nature of reality after collecting data from 10 participants. Well, maybe those 10 participants aren't just fully representative of the population. Maybe if you collected data from 20 participants, it would be, in fact, enough power to detect an effect of a given size. Remember, I mentioned that if we have if we know the effect size, then that's also part of the puzzle, right? So that's the thing. If you have very few participants but a very large effect that's easy to detect, you don't need that many. But if it's a small effect, then that's where it becomes important to have enough participants, because if you collect enough data from them, then you start to see that the participants who are getting one type of therapy are seeing a small improvement compared to another type of therapy, just as an example. And there, if you want to know whether it's an effective therapy, well, you have to look at the effect size as well. But the more participants you have in each group, the easier it is to see whether there is a difference between them. So you always want to make sure that you have enough power, i.e. enough participants in your design to truly be able to detect an effect if it really exists. And again, I also touched on this earlier, but the consequences of an underpowered study is that you can't logically know whether the effect doesn't exist or if it exists but your study was underpowered, right? So just to have this in black and white, that's what we're kind of dealing with in terms of what power really can tell us. And also, if you have an underpowered study, you also have ethical considerations. So if your study is conducted, you put participants in harm's way without the hope of a valid conclusion. If you plan to collect data from not enough participants, you're exposing them to potentially dangerous, triggering questions, any kind of adverse consequences. But if you know that you're looking for a small effect, and you know that you're only sampling 10 people, then you can be pretty sure that you're only exposing those 10 people to these undue threats without any hope of detecting a significant effect if you're looking for that small effect, right? And the last point here, it's possible that a potentially effective treatment may be overlooked. Again, if it's a small improvement, but it's a real improvement, it still could be worth it to pursue. But if you expose your participants to a study that is going to be effective, you want to make sure that you're actually collecting enough data to know that that's the case. Okay, so just to quickly sort of summarize what we've looked at so far, we've got two issues here, right? We've got the state of the world on one hand, and we've got your observation, right? The finding of the study. And these two can be at odds, right? So first off, let's just look at, if in the real world the effect is present and your study finds that the effect is present, great. You reject the null hypothesis. This is where, we're always looking for that p is less than 0.05 finding, right? Similarly, if in the real world the effect is absent and your study finds that it's absent, then you're in the ballpark of failing to reject the null hypothesis, or just for short, retaining the null hypothesis that there is no difference between your groups, that there is no effect of a treatment, that there is no differences out there. But again, if your study finds that there is no effect, but in the real world it is present, well, then you've committed a type 2 error, right? You've missed the effect. And this is where we're going to focus in on what power really is able to help us out with. And then, of course, the type 1 error, the false alarm rate, this is where, the effect is absent, but you say that it's present, right? Your data indicate that it's present, and this is where the type 1 errors are. This is where your p-value is protecting you against that. So our desired outcomes, as you know, the p is less than 0.05, and we also want to make sure that we don't neglect the probability of a type 2 error, right? That's also very important. So that's where we have to make sure that we're covered on both fronts. Now, I've talked about what happens when you don't collect enough data, right? But there's also the flip side of this argument, which is what happens if you collect too much data. And I mentioned that the more data you collect, the more precise your estimate, the more power you have to detect the effect, right? We've covered that. Another issue is that the clinical significance of a statistically significant effect may be non-existent. So on the flip side, you may, that should say may, not my, expose too many participants to potential danger. So I'll give you an example of a study that was conducted a couple years ago in using Facebook data. So what they did is they sampled over 600,000 Facebook users. And what they did is they manipulated the content that people saw in their feeds, whether it was using sort of positive words and negative words. So people would be exposed, users were exposed to either more negative content in their feed or more positive content in their feed. And then they looked at whether or not people ended up using more positive or more negative words in their own post after being exposed to more negative content in their own feeds. So what they found is that, yes, there was a significant difference between groups that saw positive and negative content. But you know what? The effect size was minuscule, just tiny, 0.06% difference in the amount of negative words. So great, they got that p is less than 0.05 value because the two groups are, it's easy to see with that many participants, how many words on average people use that are negative. But I mean, what's the difference, right? Who cares if it's 0.06%? It's less than 1% of 1% of a difference. So it's not really all that meaningful. Yet at the same time, they exposed 600,000 people to potentially triggering adverse consequences, right? If even one of those 600,000 people has some kind of, adverse consequence, then, you've done a very unethical thing. And in fact, what happened to Facebook is that they did get slammed in the media for ethical violations and things of this nature. So it's very important to not to collect enough data, not too much data. In addition to all these kinds of ethical issues, of course, if you're trying to collect too much data, that can be costly, it can be time consuming, and who has time for that? You want to collect enough data. Now the question is, okay, where do you draw the line, right? How do you know whether you've collected enough data? How do you know how much data to collect in the first place? How can you predict how much data you're going to need? And the answer to that lies in that other piece of information, which is the effect size. The idea is that and I'll get to this in more detail later, but you want to basically establish what you're expecting by reading previous literature. But just to sort of give you a broad strokes definition of effect size, it's a corollary of alpha, of that p-value, which tells you whether an effect is significant, right? The effect size tells you the magnitude of the effect in addition to its significance, right? Like I just kind of mentioned with that Facebook example, with enough data, a 1% change can be significant. But with not enough data, a 50% change might be evaluated statistically as non-significant. So the idea is that even if you have a p-value greater than 0.05, the effect size is still informative. I can't tell you how many article submissions I've reviewed as a peer reviewer where people say, oh, look, we got a p-value of 0.06, it's not significant. We got a p-value of 0.04 over here on this other effect, it's significant, and so we have implications for treatment or theory, and that's not the full picture. And I always tell students, I always tell authors, you have to focus on effect size. This is becoming, over the last 10, 20 years, a requirement for APA journals, and so certainly you shouldn't ignore it in your dissertation. And we'll look at examples of effect sizes later on in the presentation. There's a lot of different ones. There's only one type of p-value, but there are many different types of effect sizes. So we'll look at those because it will become very important for you to know what to look for when you're establishing your own required sample size. So this is the question. How many participants do you actually need? How do you know you're collecting enough data, not too much data, right? And this is determined by 3 inputs. Your chosen alpha, the p-value, which we typically set at 0.05, your chosen power, which we typically want to get to 0.8, and the expected effect size. Okay, so we'll look at expected effect size in a minute, but just to recap, remember we're interested in we want to avoid type 2 errors. We want to avoid missing effects if they're real, and we also want to avoid concluding that effects are real if they're not. So that's what alpha and power tell us, whether we're actually doing that. So you want to make sure that your alpha is less than 0.05 and your power is greater than 0.8. Those are basically the gold standards like we looked at. Now the expected effect size, this is the real sort of linchpin of this entire process. So what do you mean expected effect size? What is that? The idea is that you review previous literature studying similar constructs to the one that you're interested in. And It doesn't have to be, the exact same study that you're trying to conduct, because that would just make your study redundant. But something that's very similar, something that is either related conceptually or uses the same instruments, like the multiphasic Minnesota personality inventory, MMPI, or what have you, and studies a similar population, then you can kind of get an idea of what's going on out in the real world, right? The state of the world that we've looked at in these diagrams here. And then you look at a couple of different things. You look at the sample sizes that they used, and then you look at the effect sizes that they report in this previous literature. So there's a number of different things that can be reported. This is just a list of the most common ones. Cohens D and Hedges G are two versions of effect sizes where if you're comparing two groups, that's what would be reported. Eta, or eta squared, you see it looks like this lowercase n. And partial eta, that's what this little p stands for, is partial. These are where if you're doing a comparison of multiple groups, not just two groups, that's what the effect size would be. Omega is used in other kinds of studies as well. It looks like a W. And then you've got Pearson's R. Now, you might be wondering about Pearson's R, actually, because, like, isn't that a measure of correlation? And yes, the answer is yes, it is a measure of correlation. And the closer to 1 or -1, the stronger the correlation and the larger the effect. And the closer you are to 0, the smaller the effect, right? And the same holds for all of these. Is the higher the value, the bigger the effect. And a negative value simply means that you're comparing, group 2 to group 1 versus group 1 to group 2. So a negative effect size means nothing. It's just the magnitude of it is what's important. So really the deviation from 0. Now, notice if we go back to this point here about the sample size used, people can report or previous studies can report a non-significant effect, right? But if the effect size is large, you have to make note of this, because if it's a non-significant result, but it's a large effect, you have to think, okay, well, these folks used a sample size of 20. That to me suggests that I have to use a larger sample, because if I use a larger sample, then I'll get significance and a large effect size. Anyway, okay. So finally, the statistical tests used in previous lit do not have to be identical to those appropriate to your study's design. So if a previous study ran a correlation, but you want to do a study comparing two groups, you can still do that. There are different ways to look at effect size where you're saying either it's small, medium, or large, or you can get even more precise and say, okay, if it's this size correlation, then I can get, an effect size for my design that I want to do. And that's what this next slide is all about. So if they don't report effect sizes, if it's an older study, you can use other values to calculate. There's a really good study in the Journal of Pediatric Psychology from 2009 by Durlak, where this author shows how to, well, select, calculate, and interpret effect sizes. So I highly recommend reading this. And in there, specifically, you're shown how to convert Cohens D to Pearson's R and vice versa, and obtain Cohens D and Hedges G from means and standard deviations that would be reported in a previous study, even if it doesn't report effect sizes. And then finally, they also, Durlak also shows how to calculate Pearson's R from students T. That's a t-test, and vice versa. So you can access the article, and there's also the full text is available online for free, so you can track that down. And there's also a very handy calculator if you want to skip all that and just if you want to do calculations of Cohens D to Pearson's R, you can use this calculator that's available that was created by David Wilson at George Mason University. Okay, so those are ways to kind of track down the effect size that you would expect. And what you can do with that information is say, okay, if I'm expecting, a small effect size, I know I'm going to need more participants. to get a statistically significant result that is not underpowered, so that you have sufficient power by way of enough participants. And again, that's how you can find an effect size based on previous studies, right? You look at a previous study and you see, okay, well, they reported this effect size, I can use that. Or if they reported, partial information, you can use the information on this slide to basically obtain an effect size that you can then plug into your expectations. Okay, if all else fails, obtain a range of sample sizes necessary for a range of effect sizes. So let's say that there's no previous lit, right? And you just have to kind of take a best guess at what's going to be happening in your study. It's best to assume you're going to obtain a small effect. Worst case scenario, assume a medium-sized effect, and I'll get into what all that means. Because basically, as I mentioned in this little sub-bullet, large effects are obvious, and further scientific inquiry would be more redundant than useful. So, you can say that, you can have a hypothesis that males are on average taller than females. Well, great, that's already established. We know that, men are going to be about, 6 inches or so taller than women on average. So no big deal, right? What's the point of conducting another study on that kind of finding? So again, it's important to consider only small to medium effects as your expected effect size. And Cohen has a very, very, very good resource that can help with this. It's called a power primer. He's the king of this kind of work. His work has been cited literally tens of thousands of times. So it's very important to check out this article. You can download it from the EBSCO database that we have access to through the Chicago School Library, and certainly have a read through there. What I want to do here is just kind of focus on a bit of a summary. I keep talking about what are these small effects, medium effects, what is all that? Basically, this is a table taken from Cohen's 1992 article, and this kind of breaks down what it means to have a small, medium, or large effect when you're looking at previous literature. So essentially, let's say a previous study found an effect size across 2 groups of 0.3. Okay, that's Cohens D right here, because you've got 2 groups. M sub A versus M sub B means the mean of group A versus the mean of group B. Okay, and then you get a Cohens D value ranging from 0 to basically infinity, because what it means is it's the number of standard deviations apart that 2 group means are. So basically, long story short, if you get a value of 0.3, that means it's somewhere between a small and medium effect, right? It's greater than 0.2, it's less than 0.5. You call that a small effect. But the main idea here is to make sure that you're using that information to then guide your data collection. So regardless of what type of study you're running, there's all kinds of different type of effect sizes that are listed. So here, for example, you've got F squared, which is used in multiple regression studies, F, which is used in one-way analysis of variance, or ANOVA, where you've got, say 3 or 4 groups that are being compared on some measure. You've got chi-square, you've got proportions tests, all kinds of different things. And here's an important one, correlations. So basically, when you look at previous literature, you can start to get an idea of when they're reporting these kinds of effect sizes. You can use those as a guide for what your study is going to need to do. Again, it doesn't have to be identical. If a previous study ran a 2-group design and you want to do a multiple regression, but you know that they found a small effect size, you know that you're expecting a small effect size, so that you have to translate it into your own scale, as it were. But you still know that it's a small effect, which is very important for designing your study. So let's look at how that might actually pan out without doing any calculations by hand. What Cohen did, again, this is that same article, I'm just kind of pasting in his table 2 here. As you can see at the top, it's table 2 from his study. You basically get a list of expected sample sizes that you would need. Okay, so basically, let's say that you now know that you're expecting a small effect, and you know that you want to run an ANOVA with 3 groups, right? That's what 2G, 3G, 4G, that means how many groups you have. So, okay, I'm expecting a small effect, and okay, so right, so there's also alpha. So if you have a very strict p-value, then you're looking at these 3 columns. We're typically only looking at p as 0.05 as being that criterion of avoiding type 1 error. So, okay, let's say you're expecting a small effect, and you want to run an ANOVA with 3 groups, right? So you follow this column down until you get to the 3-group row, and you know they need 322 participants. Okay. Now, this is in fact 322 participants per group. So that means you're looking at about 900 people in your study if you want to have sufficient power to conclusively say that, you know, a statistically significant effect is real. That's a lot. So this is where we start to get into design implications. But before we get into that, I want you to note something very important, that once you get into medium effect size, you only need 52 participants per group. It's like, well, that's easier to detect that effect, right? If it's a medium-sized effect, it's easier to detect. So it's very important to know what the previous literature is telling you about the phenomena, about the constructs that you're interested in. Because if you know that they're all showing, okay, well, you know, study 1, 2, and 3, they all show, you know, medium effects. That's very encouraging because you know how to plan your study. But if they're all saying, look, it's a small effect, it's a small effect, it's a small effect, then you know you're at least in the ballpark of small effects, and you know that you have to plan ahead for more data collection. Now, as far as implications for your design, can you cut your study down from 3 groups to 2? That would certainly help you if you're expecting a small effect, right? Instead of collecting, what, 322 times 3 is, I'm just going to pull out my calculator. I'm not going to be doing that in my head. But 322 times 3 is 966 participants. Well, maybe that third condition isn't all that important for your really core question of interest. Well, what's 393 times 2? That's 786. So you're saving yourself a really big headache of an additional 180 participants if you can, you know, remove that third condition if it's not super important. So essentially, you know, it's another way to think about how to go about putting your study together. It all starts with previous literature, knowing what to expect, and then using that information to plan your own study that's going into like uncharted territory, right? And I see that there's a question, number 8 is multiple regression. Dr. Du already covered that. Yes, it is. Except here, with multiple regression, you're not talking about groups, you're talking about variables. Because with regression, you're putting in multiple predictor variables with one outcome variable. So this is how many predictors you have, whether it's 2, 3, 4 predictors, so on and so forth. And it's the same kind of issue. You know, if you can eliminate one of your predictors because it's not super important, you should think about doing that because it, again, chops down the number of participants you would need to get a viable study. Okay, so this is a good sort of place to start. You start with this table here in Cohen to make a prediction about how many participants you would need. There is also another way that you can do this, which is a software called GPower. And GPower allows you to get much more precise estimates where Cohen gives more generic examples, right, with small, medium, and large. Well, what you can do is build more precise estimates using GPower. So, for example, I'm just going to, you know, you can download GPower from this website that's listed on here. I already have it downloaded, so there it is. Basically, just to corroborate what Cohen is telling us, I'm going to go to tests, means, and I'm going to do, you know, an ANOVA, right, many groups ANOVA one way. So notice he has, actually, let me go back a slide. That'll be a little bit easier to see what's going on. So remember, so he's got 8 different tests that he's showing, because these are the most common types of tests that are conducted in psychological studies. But you'll notice that GPower has tons of different tests that you could run that Cohen doesn't cover. So keep that in mind, because if your study ends up requiring a different kind of design than what Cohen provides, then you can certainly use this software to get what you need. But just for the sake of demonstration, I'm going to ANOVA one way, which is what this is here, number 7. And basically, I already know that a medium effect size of 0.25 is what we use, right? So you look at, well, let me move this out of the way. You look at, let's see, where is one-way analysis of variance, right? Here we are, number 7. Medium effect size is 0.25. So, okay, I'm going to tell GPower, plug that in. I want my alpha at 0.05. I want my 1 minus beta, that's the power, at 0.8. And let's say I have 3 groups, right? So it tells me, let me just go back. It tells me, okay, you're going to need 159 participants. Now, okay, how does that jive? I mean, I thought that with 3 groups and a medium effect size, I need 52 participants. Well, that's the trick, is Cohen tells you how many per group, right? What GPower does is it tells you total. So in fact, if we say 52 times 3, we get 156. And this is, you have to add 3 because of what are called degrees of freedom. But anyway, you see that it's 156 here. So it checks out. Now, what if you have a study that's super informative? Well, guess what? You look at the previous literature, they report an effect size, and they say, oh, no, guess what? We found an effect size of, 0.4. 0.43598, whatever the case may be. It's a much more precise estimate, right? And then what sample size you would need per group, which is still close, to what Cohen is telling us. But now you can do it much more precisely by plugging in what the previous literature has found to be the case. And again, you can determine effect sizes from different pieces of information. So let's say that they don't report effect size in the previous study, but they say, okay, group 1 had this mean, it had this many participants, so on and so forth. You can plug all that in and then calculate and transfer to main window, and it will plug in the effect size, and then you can calculate your required sample size. Now, of course, this can get pretty tricky pretty quickly. So if you're going to be going down that road, let me know. I can help you out with all that. And certainly if you're having trouble interpreting Cohen or any kinds of issues like that, again, let me know. That's what I'm here for. With that, this is the contact information. We have a YouTube channel where this is going to be available. I'm actually going to stop recording now.